Okay, so thinking geometrically about least squares is something that's very useful to develop intuitions about what it's doing. It's not necessary in order to use it or to even do mathematical things with it, like analyze it, but intuitively it can be very helpful. So in the next couple slides, I just want to build some intuition about what least squares regression is doing geometrically. So as we discussed before, we want to minimize something that looks like this, where we take all of the outputs y and put them into a n-dimensional vector if we have n observations. And we approximate that with this matrix vector product. So we have the matrix X, where the ith row corresponds to the ith input vector, or some function of it. And the weights then are what we want to learn. So we can think of y as some point in Rn, a very high dimensional space if we have many observations. And what we're trying to do is find a vector w in order to get this matrix vector product physically close to the vector y in Rn. So remember that this matrix vector product really entails taking the jth column of the matrix X, written this way, multiplying it by the weight wj, which is just a scalar. So we take the vector xj, jth column of X. We then scale it in some way according to wj. So if it's wj is positive, we stretch it or shrink it, but keep the direction the same. If wj is negative, then we flip its direction and stretch it or shrink it. We do this for each column of the matrix X, and then add these vectors up. So xj is pointing in one direction, xj plus 1 is pointing in another direction. We add those up, and we're trying to now make the sum of these vectors get as close to y as possible, which is a point in Rn. So what least squares is doing is it's basically saying the best vector w is the one that gets the sum of these vectors as close to y as possible according to the Euclidean distance, which is the intuitive direct line. So the vector constructed from xw gives me a point in Rn, and then I basically say what is the squared length of that point to the point I'm approximating, which is y. So I draw a line between the two, and I return the squared length of that line, and that's equal to the sum of squared errors. I'm trying to minimize that, so I'm literally trying to make the distance that I would have to travel in a direct line from my approximation to y as small as possible. So here's an illustration of that. In this case, we have, because I'm trying to show it, we can only show it for 3 observations. So y is a vector in R3, meaning that we have three data points. x1 is the vector of 1s, the first column of X. So this is a vector of 1s. So this point here would be 1, 1, 1 in R3 according to some axis. And x2 is then the second column of the matrix big X. So we're assuming that our data points are in R, our inputs are in R, and we have 3 pairs, x1, y1 through x3, y3. And so here's the first column of our matrix X, the second column of our matrix X, and we're now trying to weight these 2 vectors to get them as close to the output vector y as possible. So if we have 2 columns to X, we basically have 2 vectors that we get to play with in R3. So of course, unless it's very rare that we could take 2 vectors in R3 and actually hit this vector y in R3. We don't expect to be able to do that. So what we're trying to do is, in this 2-dimensional space spanned by these 2 vectors, find the point that is physically the closest to y as possible according to the everyday Euclidean sense. So in this case, what we're saying is take y and drop a line, a straight line, to the two-dimensional space spanned by these two vectors, so 90 degrees. This point here is physically the closest that we can get the sum of these two vectors to the vector y. And this is the least squares solution. And so that's what we have here, that when we take the least squares vector WLS, it's a two-dimensional vector for this particular case. What we're saying is take the first dimension, multiply it by x1, the second dimension, multiply it by x2, sum those up, and you'll hit this point. That's the approximation y hat of y. That's the closest that we can get those two, the sum of those two vectors to be to the output y. So there are two visual representations that we've discussed about least squares. I'll show them to you here just to differentiate between the two. So in the first representation, what we showed was a two-dimensional input and the corresponding output y, and we showed them as points. So here we have roughly 10 or so points where the input is two-dimensional. So this is the input, say this point here, and then the output is that point there along this dimension y. And we're showing all of the points in this case, and we're representing the linear regression function as a hyperplane like this. So this is the function that's represented in this picture. So something like this can be shown for all n, but only when the data is in R2 or R1 if we want to include the so in R2 where So something like this can be shown for as many points as we want. The data is in R2, and then the offset, the shift of this hyperplane is corresponds to the weight W0. In this case, we're representing all of the y's in one vector. So here we have different values for y, the output according to the input. Here we stack all of the outputs together, and then we represent each dimension separately for all of the points. And so in something like this, we can only show 3 points and one-dimensional data if we want to also represent the DC offset. So these are two ways that we can visually represent them. They're fundamentally different. Each have their own intuitions that help you think about the problem, and both are very useful, but they should be kind of separated in your mind when you think about these problems.